Hello, everyone. My name is Ethan Williamson, and today we're going to be talking about the Whisk Wheel Company from Case Study 6.1. So, a little background about the Whisk Wheel Company. They have just been called in by their largest customer, Rosewood Bicycle Incorporated, that Whisk Wheel will need to dramatically improve the quality level associated with the hub operation. Currently, the operation is unable to meet their specification limits set by their customer. Um, Rosewood has been sorting through the parts on the production line before assembly, but they want to end this procedure beginning immediately. Whisk will be required to provide information about each lot of products they produce. So that's a little background information that I read from the case study 6.1. So now we move to my background and problem statement I was talking about. So the Whisk Wheel Company was what I read is a smaller sized manufacturer specialized in precision components for consumer appliances. As part of a product upgrade they wanted, the company introduced a new redesigned hub assembly of the bicycle to improve performance and durability. Then the engineering team decided they were going to focus more on the functional areas and performance metrics during the design phase of the bicycle. So, as the production began, a problem occurred. Significant challenges on the shop floor. Uh, as they were working, more problems occurred. The hub assembly design included features um, that were difficult to manufacture at the scale. This included tight tolerances, non-standard part interfaces, and limited accessibility for tooling and inspection of the bicycle hub assembly. And that's kind of my background and problem statement covered up. So for the part one chart, um, we noticed it had all the charts have 24 values or 24 data sets. So this data shows us the measurements of each hub diameter taken from 24 samples, obviously from day one, and this came from page 216. We have calculated both the average and the range. The averages are very consistent, which means the variation between each part is minimal. The data suggests that the machining process is producing the hubs within its expected tolerance, and it did produce the hub within the expected tolerance. So we see it started at 3.74 and went all the way up to 3.76. And on the bottom we have our sizes, and on the left side, the left horizontal axis, we have the number of units, and the sample parts is 3.750 plus or minus 0.05 for our first histogram. And that's a little information about the part one chart. And this was our only chart for part one. So for our X chart for part two now, we have our 2-day comparison X chart with 24 subgroups, and we have our lower control limit, our center line, and our upper control limit. So our center line goes across this staggered chart at different values ranging from 3.736 all the way up to 3.765 is where it tops out at. So this chart is a 2-day comparison, obviously using an X-bar control chart, and it helps us monitor our process stability across the chart figure. Along the horizontal axes on the left-hand side, we have our part lengths from 3.72 all the way up to 3.77. We have sequential data points, and the vertical axis shows us the measured values of a key process variable. The two sample groups we have were compared using the upper control limit and the lower control limit. These two processes help us see if the process is behaving consistently or if it's behaving erratically. The mean and the specification limits define the acceptable range for the product process. The pattern seems very inconsistent in this X chart for part 2. So for our R chart for part 2, now we see our measurements. Again, they were recorded across 24 data sets, again, multiple parts. And each trial in this R chart, our range chart, was produced, and consistent values were ranging around 3.749 with minor variation across the range chart. Data was also collected under controlled conditions across 2 separate days. The range values were then calculated from the measurements to evaluate the process variability in the R chart. And all items in this chart seem to fall within range because our control lines on the top of our staggered data lines show us that they're butting up together, so they're concise, and that's how our control lines need to be together like this. So in the bottom we have labeled our range 2, our upper control limit, our lower control limit 2, and lower control limit and lower control limit 2. And then we have going up all the way from 0 to 0.3 above our control line, we see it tops out at 0.03, and that's it for the R chart for part 2. So for our histogram for part 2, we see the histogram shows that shaft measurements cluster towards the lower range, but none fall below the lowest bin. So we see our lowest bin is in the middle, and our lowest bin is at 5, and then our highest is 12, and then we have 7. Only 3 columns. Only 3 bins. So this indicates that while most parts are on the lower end of the acceptable range, the process isn't producing measurements outside our expected limits. Overall, this histogram suggests the process is stable, predictable, and producing parts very consistent. So we see it's at 3.74 all the way to 3.75. So that's our 2-day chart for comparing each chart. And we have on the bottom our shaft links and our group numbers, and then I have it labeled at the top our 2-day chart. And this is also comparing from day 1's data with day 2's data. And for histogram part 3, we see for day 3, we move on to our day 3 data. The product length shows us a stable process. For most measurements cluster tightly around the average of 3.75. That was our highest. And the histograms confirm that the variation is very small. The middle bins contain most of the data. As we see, there's a lot more higher range with the middle data. But most of the data with only a few measurements come from around the upper and lower edges. And then we have our Z values that also support this, showing a small amount of data falling, but it still indicates a controlled and reliable operation of the histogram. histogram for part 3. And that's it for day 3 histogram. And then we have our X chart part 3, and this one's also another clustered staggered chart. So the X chart shows us the process is stable, but all the data points stay within the upper and lower control limits with no signs of special cause variation. The measurements fluctuate slightly around the center line of about 3.749 inches, but the swings are small and consistent. So we see we have from our 24 subgroups for day 3, and all the control lines are separated, and the chart or the staggered line is staying in the middle center line. So that's a good thing. So lastly, for my presentation, we're going to discuss the R chart for day 3. So the R chart for day 3 monitors the range of measurements, again, across 24 subgroups, each having 5 parts. It's used to assess process stability and detect any abnormal variation across this chart. The R chart also shows a consistent and controlled process and consistent variation across all subgroups. No cause of variation is seen, suggesting the process is in statistical control. So all in all, the chart seems very accurate and in good positioning. And lastly, our random sample we're unsure of because production, as we go through the production, we never get a production number. It gives you an idea, but it never gives us the exact number of the hubs made for the bicycle. So that's what we're questioning, all in all, to conclude this. So that's all I have for today. Thank you for watching, and have a great day.